Okay, so we're going to start talking about separable differential equations. We actually have already talked about it, but we're going to continue looking at examples of separable differentials. And in the previous lesson for slope fields, I gave you a free response question. It was actually from 2016 and asked you to do, or we worked through parts A and B. And so here's the whole question. So parts A, B, and C. Again, we already did A and B. So let's get a pen going here. We already did A and B, and so those two are out of the way. But we're taking this equation, we generated a slope field, and just for fun, I put the, oops, it keeps happening. I put the solutions in here that we looked at last week. So just for fun, threw those in there. This was the slope field we developed, and they only asked for 6 specific points. And then they asked us to find a tangent line equation to the function, so not actually finding the function, just a tangent line equation, and then using that to estimate the value of the function at 2.1. And again, if you can recall, we talked about this. This is a term called linearization, because you're pretending that the function's a line, y equals mx plus b, or you're linearizing it, which is a fun word to say. But we are now going to actually come up with a specific y equals, or an f of x, to describe the function that fits with this particular differential equation. This will only work in Calc 1 land with separable differentials. That is all we are going to look at. These are equations where you can take all the y's and put them to one side, all the x's and put them to the other. And then you put the dy and dx with the associated pieces. Last time we met in person, and then I also put the video link up on that lesson, we did one where you could cross multiply. So where you can move the y's together and the x's together through cross multiplication. This is a similar problem, and we can't do cross multiplication per se, or that would be too many steps or extra steps, but we'll show how you can still separate this thing. So let's get into it. So we've got our y prime, or we've got our dy dx, and again, oftentimes, actually almost all the time, Leibniz notation gets used because it's much easier to see how it could be separated when it literally has 2 pieces to it, a rise dy and a run dx. So what I'm going to do is I'm going to multiply both sides by dx, and that gets me, oops, this expression. And then I'm going to divide both sides by y squared, or another way to think about it is I'm going to multiply both sides by 1 over y squared. When you do that algebraically, what happens on the left is you cancel out, I'll get a different color here, you cancel out the y squared here, and you're left with just the 1 in the numerator. And then what happens over here, of course, is you have now all your y's gathered. You can do this in one step. So provided you see it, you do not need to write this as 2 separate steps. You are welcome to write it as 1. So you're welcome to hop right over from the red to the black, and you don't have to do the intermediary, but just in case it helps anyone to see what we're doing, again, it really is a 2-step process, multiplying by dx, and then, and actually I made that, and yeah, and then multiplying by 1 over y squared, or dividing by y squared would be another way to think about it. Now what we've got is we've got our equation separated. So our y's are to one side, our x's are to the other, and that's where the name comes from. So that's what makes it separable. What we're now going to do is integrate both sides. I could just pop an integral sign on both those, but I'm going to write it as its own unique step, just to indicate to AP that I know that is the actual mechanics of calculus that I'm doing, and to differentiate it, or to, I shouldn't use that term, to delineate it from the algebra steps we did to separate. So we're now going to integrate this thing. Well, the integral on the left is an ln. Technically, there's a u substitution. Usually we don't write it. So u equals x minus 1, then du is dx, and that means the integral becomes 1 over u du. We get ln of u, plus c, of course, and then we pop our expression back in. But you can just think of it as an expression, x minus 1 on the bottom. And so if we have 1 over an expression and it's to the first power, then we're going to get the ln of that expression, and plus c. And again, whether you get there through a u substitution process, which is the technical way to do it, or you get there through just acknowledging that it's an ln. It's good either way. Neither way is better than the other at this point. On the left-hand side, we have the integral of, and I'll kind of put it over here, the integral of y to the -2. And that helps me to see it. So I'm going to add a power and divide by that power. So it becomes y to the -1 divided by -1, or negative y to the -1. So I'm going to write that as -1 over y. And we've now integrated both sides. So separate the variables, did that. Integrate both sides, did that. Make sure our plus c is there, did that. If we had no initial condition, I suppose we could take the reciprocal of both sides to get y all by itself. But if we had no initial condition, this would be as far as we could go with it from a calculus perspective. However, we have been given a specific initial. And I'm going to go back up to the problem and just grab it. F of 2 is 3. So I'm going to write that down here. So our initial condition, and let's see, let's pick our red color, is 2, 3. So that's the thing we're going to use to find c. So we're going to use that initial condition to find c. So I'm going to take 3 and put it in for y. So that's a -1/3. I'm going to take 2 and put it in for x. And I'm just going to hang on to these absolute value bars. They aren't super important because what's in there is positive, but it also doesn't hurt to have them. So that's the ln of 1, and the ln of 1 is 0, which means c is -1/3. So I've now used the initial condition to figure out what c is. So I'm going to pop back to the black pen I was using, and we're going to say, okay, I can swap out c, and in its place, put -1/3. Then I'm going to divide both sides by a -1, or multiply both sides by a -1, however you want to think about it, to get rid of the negative that's with the y. And that would make a negative ln of x minus 1 plus 1/3. You can write it this way, although convention typically is take the positive number and set it out front of the negative term. It is not necessary to reorder it. You can leave it in either of these two fashions before we do our next and our final step. And so our next step, or our final step, would be to reciprocate both sides, or to go 1 over on both sides. So if I flip both sides, it's going to look like this, because what you have, of course, right here is this, if you envision it, is really just this fraction that we never ever write that way, but it is this whole thing over 1. And if that equals 1 over y and we flip both sides, then that 1's going to be up top, and the entire expression is going to be on the bottom. And I know that makes a lot of people who've come through the algebra sequences, which is what it takes to get to calculus, uncomfortable, because you see that fraction in the bottom. If you want to get that out of there, you can. And it is not necessary, but if that just makes you, at the end of the day, feel like a more complete mathematician, by all means, what you're going to do that, and again, I want to be clear, that's not necessary, but you could multiply the top and the bottom of this thing by 3. You'd have a 3 on top, and then that 3 on the bottom is going to get arced to both pieces. When it hits the 1/3, it becomes a 1, and when it hits the ln, you just have a 3 out front. And again, this is by no means necessary, by no means better. In fact, the AP released answer, which I included in the solutions section for this, actually leaves it in this first format. So it is totally okay. And the one additional thing that happens on this one, and again, I don't want to get lost in this little nuance here at the end. I want to make sure that you understand that this is the benchmark. Being able to get the problem through to here is what the College Board, or what AP expects you can do. It's what it means to separately differentiate something. However, what happens is this really minor point, but it is significant, or it is true, is the AP will drop those absolute value bars, and they'll put curved brackets in, call this the answer. It's no more or less technically correct to have absolute values or not. However, the reason they do that, and again, I want to be clear, I don't want you to get hung up on this last step or last thought, provided you can get it to our boxed in solution over here. But the reason they do that is if we go back up to the slope field, which is up here by our little happy face where we began, we have a point at 2, 3 as our initial condition. That means on the slope field, we're up here. They didn't ask us to draw a slope for it, but that's the starting or initial value. What happens on this particular slope field is the x-axis is a spot where all the slopes zero out. In addition, the line x equals 1 is a place where you can't have a slope or where you have a vertical slope. These are really small nuances, but if you look at the differential equation for x values of 1, it creates an undefined situation or an infinite situation. That's where you have an asymptote on a graph. That's what calculus is showing the asymptote as. And so in that case, we just have an undefined location on the graph, oftentimes in the form of an asymptote. And then along the x-axis itself, where y is 0, this thing has 0 slope. So if this thing ever did get down to the x-axis, it would not cross it because it would flatten out. So the slope, when it hits that spot, flattens out. You're also not going to jump over this odd kind of asymptote feature of the graph. And so what's going to happen is you're going to be bound up here in the first quadrant. So your values, because you start right there, are going to be in the first quadrant. They can't pass this band of 0 slopes because your graph, when it hits that, is going to flatten out. You're also not going to move past this asymptote. So you're stuck up here, and up here is an area where there are x values that when you take and subtract 1, you're always going to get a positive because, again, you're not going to puncture through that asymptote, and you're not going to cross down into negative y values. So because of that, anything that you put inside those absolute values is going to be positive. Again, it's a really, really minor nuance. I don't want to get lost along the way in terms of what you're able to do, but it's also important to note when you see that and the AP has dropped absolute value bars. So what I'd like you to do now is work through the second problem on that practice worksheet, and then I'm going to put up a video for you to check your work and follow along with what I'm doing on a very, very similar type problem.